Good morning, everyone. I am Ravini Kumar, second MSc Mathematics, and my topic is Fibonacci operator and its application under the guidance of Dr. Gilberto Anthony Xavier, Associate Professor, PG and Research Department of Mathematics, Sacred College, Tirupattur. Contents: Introduction, Fibonacci operator, Fibonacci summation using exponential functions, application of Fibonacci-Nabla operator, conclusion, references. Introduction. In this project, by expanding the exponential function to the exponential function, a third-dimensional second-order summation formula is developed for the product of the exponential function and polynomials using second-order Fibonacci numbers. For each a1, a2, a3 of real numbers, a three-variable Fibonacci sequence is defined as f of a1, a2, a3 is equal to 1, f of a1, a2, a3 is equal to a1. In general term, f of a1, a2, a3 is equal to a1, f of a1, a2, a3 plus a2 into f of a1, a2, a3 plus a3 into f of a1, a2, a3. This is equation 1. By taking a1, a2, a3 is equal to 1 is the well-known Fibonacci sequence. Remark: for convenience, we denote fn of a1, a2, a3 as fn. Definition 2.2. Let u of tau belongs to 0, infinity, be a real or complex valued function, and L greater than 0 be fixed. The L difference operator del L on u of tau is defined as equation 2, and its inverse is defined by equation 3. Definition 2.3. For a L tau belongs to minus infinity to plus infinity, and n belongs to n of 0. The L polynomial's factorial is defined as equation 4. For real nu is defined equation 5. Definition 2.4. For minus 1 less than L less than 1 and tau belongs to minus infinity, less than infinity, the L actual function expressed as the E of tau of L is defined as equation 6. In general term, is defined as E of V of T of L is equal to 1 divided by gamma of 0 plus 1 plus tau L of divided by gamma of V of plus 1 up to infinity. Definition 2.5. Let u be a real valued function. The Nabla L difference operator del A of L on u of tau 1, tau 2, tau 3 is defined as equation 7 and its inverse is defined by equation 8. Example 2.6. Let 1 minus summation j equal to 1 to 3 aj e of j L1 into L1, e of j of L2 into L2, e of j of L3 into L3 not equal to 0. By 7 and 8, we get equation 9. Theorem 3.1. Let fn express the nth span of the two parameter Fibonacci sequence provided equation 1, and v of tau 1, tau 2, tau 3 be a solution of the equation tau nabla of v of tau 1, tau 2, tau 3 is equal to u of tau 1, tau 2, tau 3, v of tau 1, tau 2, tau 3 belongs to r square. Then we have v of tau 1, tau 2, tau 3 minus fn into fn minus 2 plus a2 fn minus 1 plus a3 fn minus 3, and this is the equation 10. Corollary: if summation j equal 1 to 3 aj e of j into L, e of j into L2, e of j into L3 not equal to 1, then we have equation 12. Example: taking tau 1 is equal to 1, tau 2 is equal to 2, tau 3 is equal to 3, n equal to 3, a1, a2, a3 equal to 2, L1, L2, L3 equal to 1. In equation 12, we get 615488. Remark: for accessible, we denote E of ISL is equal to E of I into S into L1, E of I into S into L2, E of I into S into L3. Corollary: if V of tau is equal to summation A into L inverse tau 1 power m1, tau 2 power m2, tau 3 power m3, E of F tau is an exact solution of 18. Then equation 13 is taking u of tau 1 tau 2 tau 3 is equal to tau 1 power m1 tau 2 power tau m2 tau 3 power m3 e of st in theorem 3.1, we get equation 13. Example 3.6, the following example for verification of equation 13. If tau 1 is equal to 2, tau 2 is equal to 3, tau 3 is equal to 4, n equal to 3, m equal to 0, and m1, a1, a2, a3, l1, l2, l3 are 1, then equation 13 becomes, and the final solution is 5518336. Theorem 3.7, let u of tau 1, tau 2, tau 3 and v of tau 1, tau 2, tau 3 be the real valued function. Then the equation 14, for accessible, we indicate e of il is equal to e of il1 into e of il2 into e of il3. Correlate 3.9, at e of tau 1, tau 2, tau 3 and v of tau 1, tau 2, tau 3 be the real valued function. Then the equation 15. Correlate 3.10, an exact solution of the second order discrete equation is given by equation 16. Theorem 3, corollary 3.11, if v of tau 1, tau 2, tau 3 is equal to nabla inverse of tau 1, tau 2, tau 3, e of tau is an exact solution is given by equation 16, then the three-dimensional Fibonacci summation formula for tau 1, tau 2, tau 3, e of tau is given, equation 17. Example 3.12, let tau 1, tau 2, tau 3, a1, a2, a3, l1, l2, l3 equal to 1, n equal to 3 in equation 17. Then we find the final answer is 1076744. Application of Fibonacci-Nabla operators. A system whose motion is controlled by the difference equation Nabla of v of tau 1, tau 2, tau 3 is equal to tau 1 power m1, tau 2 power m2, tau 3 power m3 e of s tau. Theorem 4.1, if the system satisfies the condition summation j equal to 1 to 3 aj e of j into s into l not equal to 1, then an exact solution of the three-dimensional difference equation nabla of a is l v of tau 1, tau 2, tau 3 is equal to tau 1 power m1, tau 2 power m2, tau 3 power m3 e of s tau is given by equation 18. Conclusion, the external function is used to solve a particular category of three-dimensional second-order recurrence relation with the Fibonacci difference operator. By substituting external functions for exponential functions, the inverse of the Fibonacci-Nabla difference operator yields multiple outcomes on the sum of a finite series and in addition to several applications in the field of biology. These are the references of this my project. Thank you.